Two baseballs are thrown from the roof of a house with the same initial speed, but one is thrown upwards and the other is thrown downwards. Compare the speeds of the baseballs just before they hit the ground. Now, the balls will not hit the ground at the same time, but they will have the same speed. To explain this, I need a little bit of space. All right, let's analyze the motion of both balls. So we have, move those over. Okay, we have the ball that's thrown downwards. This one's easy. It's thrown downwards with an initial velocity. It falls a certain height. Oh, it takes a certain amount of time. It's going to land with V final. That's straightforward. What's a little more complicated is the ball that's thrown straight upwards. So what's key is that the ball will go up, it will come to rest, it will come back down. By the way, I'm drawing it as two-dimensional, but really it's just going straight up and straight down. So this is one-dimensional motion, but I'm drawing it like this so it's clear to see. The ball will go up, it will stop. It will come straight back down and it will pass its initial position. At that point, it's going to keep falling and it's going to hit the ground. So, how fast is it moving when it's going here? Because if it's moving at V initial, downwards, it's going to have exactly the same kinematics, right, as the ball that was thrown downwards. So let's see, if it's initially thrown upwards with V naught, let's use a little kinematics here. We have V naught. We know that at the very top, the velocity is going to be 0. We also know that the acceleration of an object in free fall is going to be negative g, right? If we're saying that up is positive and down is negative, the initial velocity is positive, it's positive, and the acceleration would therefore be negative. And we want to know at what time does it hit the top? Well, we know that the time it takes to go this whole distance, we'll call that t. Therefore, this is like t over 2. Half of the time to go to the top, half the time to come back down. So the time at the top is t over 2. So we have our first kinematics equation. And what we're trying to figure out is how fast is the ball going to be going at this final position when it reaches the initial height that it was thrown from. So we want to know how long does it take to get to the top first. So that's what we're going to set up. We're going to solve this for t. So we're going to subtract v naught to the other side, divide by a. Now we know that the final velocity is 0 at the top. We know the initial velocity is v naught. The acceleration is negative g. So we can see that the time it takes to get to the very top is v naught over g. Okay? So therefore that's the t to that time to the top. So therefore the time all the way back over here is going to be 2 times that. So the full time from when it goes from here all the way to here is going to be 2 v naught over g. Now I'm going to use my kinematics equation 1 again to see how fast is it going at that time. Okay? So we're solving for v. We know v naught is just v naught. We know that the acceleration of any object in free fall is negative g. Now the time it takes to do that full path from here to there is 2 v naught over g. Okay, g's cancel. We get v equals v naught minus 2 v naught. Look at that. The final velocity at this location. So when this ball gets back to the starting location of the second ball, its velocity is also v naught, downwards, negative v naught. Therefore, this ball, by the time it reaches the same height again, will have the same starting velocity as the ball that was thrown downwards. Therefore, from that moment on, they are both accelerating at the same rate over the same distance. They have the same starting velocity from this point. Therefore, they will land with the same speed. The answer is C.